Alright, in this video we study some variations of the limit of a function, such as divergence or divergence to infinity or negative infinity or right or left limits. Okay, let's start. Okay, we have studied the limit of a function, let's say f of x, as x goes to a. If it approaches alpha, then we say the limit of f of x is alpha as x goes to a. And what this meant was this. For any epsilon that is positive, there exists some delta that is positive, and that is for all such that for all x in the domain of this function f, if the difference between x and a is between 0 and delta, then we can make the difference between f of x and alpha be less than epsilon. So this epsilon can be any positive number. So that means this can be very, very small, arbitrarily small, in fact. But still, if we take small enough delta, then this can hold. So if this is possible, then the limit is this. Now, if this is not the case, then we say there's no limit, okay? Or we say the limit doesn't exist, does not exist, or f of x diverges as x goes to a. So if this is not the case, the limit doesn't exist, or f of x diverges as x goes to a. And in particular, as x gets closer and closer to a, f of x gets bigger and bigger and arbitrarily large, then we say f of x diverges to positive infinity, or we write the limit of this is positive infinity as x goes to a. Well, to be precise, what do we mean by f of x becomes arbitrarily large? It means for any positive number, let's say m, there exists some delta that is positive, and for all x that is in the domain of the function, if x is close enough to a, so the difference between x and a is between 0 and delta, then the value of f of x is greater than m. Okay. In this case, this m can be any positive real number, but what we mean by this is m can be very large. Okay. So that means if, suppose, let's write a graph of the function. Okay. As x gets closer and closer to a, whatever the value of m is, if x is close enough to a, okay, then for example in this graph, if x is in this interval, then the value of f of x is greater than m. Okay, so this m can be very large, and however large this m is, if we get close enough to a, if x gets close enough to a, then the value of f of x is always greater than this m. In that case, we say f of x diverges to infinity. And similarly, if f of x becomes arbitrarily large with the negative sign, that means f of x becomes smaller, not smaller and smaller, but larger, negatively larger and larger. Then we say the function f of x diverges to negative infinity as x goes to a, and write limit of f of x as x goes to a is negative infinity. Okay. The precise meaning of this divergence to negative infinity is very similar to this definition. That is, in this case, we can write like this. For any m positive, there exists some delta positive for all x in the domain of f of x if the difference between x and a is between 0 and delta, then f of x is less than negative m. Okay, we say m is positive, so negative m is negative, right? So however large this m is, f of x can be less than negative m. So that means f of x is arbitrarily large in the negative direction. So it's just like a mirror image of this. So just take a mirror image of this graph. Around the x-axis, we have something like this. So we have some graph like this. Okay, let's say this is A. And so let's pick negative m. So even if this is a very large negative number, if we take x close enough to a, so that means, for example, in this interval, if x is within this interval, then the value of f of x is always less than negative m. Okay, so this is possible however large this negative m is in the negative direction. Okay, so if m is even larger in the negative direction, then if we take x closer, even closer to a, then it's still less than negative m. So that's what we mean by divergence to negative infinity. And you should check this concrete example. Consider f of x that is equal to 1 over x minus 1 squared. Okay, the domain of this function is all real numbers except for 1. Okay, it's not defined at x equal to 1 because in that case the denominator becomes 0, so it's undefined. So if you draw the graph of this function, it looks like this. So this is 1, and it diverges to positive infinity like this. Okay, so if we take any positive number m, then if x is close enough to 1, then f of x is always greater than m. And therefore, the limit of this function as x goes to 1 is positive infinity. Okay, next we define left and right limit. Limits. So when we consider limit like this, x goes to a, then we mean that this x can approach a from any sides of a. Okay, so let's say if we consider this x-axis and say this is a, then x can be on the left-hand side of a or right-hand side of a. So from either side, we don't care. For any side, x can approach a. That's what we mean by this absolute value of x minus a in the definition of the limit. And on the other hand, when we say left limit, we only consider this case. Okay, x is always on the left side of a. So left limit is we write like this: limit of f of x, x approaches to a from the left. That we express by a minus 0. So minus 0 means minus some very small positive number. So that means this side, okay, minus 0. And what we mean by this is this. For any epsilon, as usual, there exists some delta that is positive. Exists delta that is positive, and for all x in the domain of f, if so now x is on the left hand side of a, so that means x is less than a. Okay, we only consider this case. So a minus x is positive, right? Because x is less than a. So if this is, so the difference a minus x is between 0 and delta, then the difference between f of x and alpha is less than epsilon. Then we say the left limit of f of x as x approaches a from the left is equal to alpha. And similarly, we define the right limit of a function. So in that case, we consider only this part. Okay, so we write limit of f of x, x approaches a from the right. In that case, we write plus 0. Okay, so the right limit of f of x is alpha as x approaches a from the right is defined as this. As usual, for any positive epsilon, there exists some delta positive such that for all x in the domain of f, in this case, x is greater than a. So x minus a is positive. So if this difference is between 0 and delta, then the difference between f of x and alpha is less than epsilon. So if this is the case, we say the right limit of f of x as x goes to a from the right is alpha. So why do we bother with left and right limits? That's because sometimes they are different. Let's see an example. Okay, here's an example. F of x, let's say this is defined as x times x plus 1 divided by the absolute value of x. So this is defined on the domain that is all real numbers except for 0. Okay, when x is equal to 0, this denominator is 0, so it's undefined. So, but except for that point, this is well-defined function. So let's consider the limits of this function. Okay, first consider the right limit. So x goes to 0 from the right. So in that case, we write 0 plus 0, but we usually abbreviate it as just plus 0. Okay, so x approaches 0 from the positive side. Okay, so this is the right limit. Okay, so we know that x is positive. X is kept positive as it approaches 0. So that means this absolute value, if you remember the definition of this absolute value of a real number is this. It's positive x if x is non-negative, or it's negative x if x is negative. Okay, either way, it's positive. Okay, so when x is positive, then this denominator is just x. So we can just cancel this x, and we have limit of x plus 1 as x approaches 0 from the right, and that is 1. Okay, then consider the left limit, limit of f of x, x approaches 0. So technically we should write 0 minus 0, but that is usually abbreviated as just negative 0. Okay, now since x is kept negative, so this denominator becomes negative x. So x times x plus 1 divided by negative x. So this x cancels, and we have x approaches 0 from the negative side, and we have negative x plus 1. So this limit is negative 1. So as you can see, these limits are different. The right limit is positive 1. The left limit is negative 1. And you can clearly see these limits if you draw the graph of this function. So let's draw the graph of this function. And what does it look like? Okay, when x is positive, then as we did here, we just have x plus 1. So that is the function here on the positive side. And when x is negative, we have this. So that is negative x minus 1. So this is positive 1, and negative 1 is somewhere here. So negative x minus 1 looks like this. Okay, so this is the graph of this function, f y equals to f of x. That is x times x plus 1 divided by the absolute value of x. Okay, so if you move x from the positive side, okay, then the value of this function converges to positive 1. And if you move the value of x from the negative side, then the value of this function converges to negative 1. So that's what we have here. Let's see another example. That is f of x, 1 over x. So what is this? And let's consider the right limit of this function. X goes to 0 from the right. Then maybe it's easier if you draw the graph of this function. So this function looks like this. On the positive side, it's this. On the negative side, it's this. So as x gets closer and closer to 0, then this function becomes larger and larger, and it diverges to positive infinity. And if x approaches 0 from the left, then so x is always negative, so we have negative 1 over some negative small number. So x diverges to negative infinity. 1 over x diverges to negative infinity if x approaches 0 from the left. So in this case also, the right and left limits are different. Okay, next we define limits at positive or negative infinity. Okay, so for example, limit of f of x as x goes to positive infinity. If this converges to alpha, then what we mean by this is the following. That is, for any epsilon that is positive, there exists some delta that is positive, such that for any x in the domain of the function f, if x is greater than delta, then the difference between f of x and alpha is less than epsilon. Okay, so this part is different from what it used to be, because we are now considering x becoming larger and larger, and arbitrarily large. So that is expressed by this. So usually, if we say delta, that usually means some small positive number. But in this case, delta can be arbitrarily large positive number. So for example, if we have some graph like this function, so it converges to some value, let's say alpha. And if epsilon is very small, then the difference between this and this, then so alpha plus epsilon is here, and alpha minus epsilon is somewhere here. So in this belt, if delta is large enough, then for example in this case, let's say if delta is something like this, if x is greater than delta, then the value of f of x is within this band. Okay, that's what this means. So even if epsilon is very small, so becomes narrower, we can always pick some greater value of delta, and above which the value of f of x lies within this narrower belt. And similarly, we can define the limit at negative infinity. Okay, x goes to negative infinity. This converges to alpha. That means for any epsilon that is positive, there exists some delta that is positive, such that for all x in the domain of f, if x is less than negative delta, so delta is positive, so negative delta is negative, then the difference between f of x and alpha is less than epsilon. So in this case also, this delta can be arbitrarily large. So this negative delta can be arbitrarily large negative value. So if x is less than that large negative value, then the difference between f of x and alpha is always made to be less than epsilon. So if this is the case, then we say the limit of f of x at negative infinity is alpha. Okay, let's see a little theorem here. Now, theorem. Suppose we have a function f of x defined on an interval that is an open interval between a and b, such that the right limit of f of x as x approaches a from the right is alpha. Okay, this a is this a. Okay, that means the lower bound of this interval. Then the following holds. If there exists some constant, a real number, such that for all x in the interval, f of x is greater than or equal to c. Okay, then alpha, this limit, is greater than or equal to c. And similarly, if there exists some constant d such that for all x in the interval, f of x is less than or equal to the d, then the limit alpha is less than or equal to d. Now let's prove this theorem. I only prove part 1 here, and the part 2 is very similar. And we prove this by contradiction. Okay, so here's the proof. So since we are proving by contradiction, suppose that this is not true. That means suppose that alpha is less than c. Okay, so then we so c minus alpha is positive. So let's say epsilon, we define epsilon by c minus alpha, which should be positive because of this assumption, right? But we are assuming that the right limit of f of x as x goes to a from the right is alpha. So the alpha is the right limit of f of x. So that means there exists some delta such that for all x in the interval, if x minus a, so since we are considering only the right limit here, there is no absolute value here. If this is true, then the difference between f of x and alpha is less than epsilon. Okay, but now this means therefore f of x minus alpha in particular is less than epsilon. Actually, we also have this part, but we don't need it. So this should hold. Therefore, f of x is less than alpha plus epsilon. But epsilon was defined as this. So this is equal to alpha plus c minus alpha, which is c. So that means f of x is less than c if this is true. Okay, but this contradicts our assumption that f of x is greater than or equal to c for any x in the interval. So this is a contradiction. Therefore, our assumption was wrong, and the negation of this is true, which is alpha is greater than or equal to c. And we are done. Okay, next theorem is an exercise. So if you understand the meaning of limit and right limit and left limits, then you should be able to prove this. Okay, so suppose f of x is defined on some interval such that a is in this interval. Okay, so if the limit of f of x as x goes to a, so this is not right or left limit, it's just limit, okay? If this is alpha, so this is equivalent to the following. Limit of x as x approaches a from the right is alpha, and the left limit x approaches a from the left is equal to alpha. So this, the right limit is alpha, the left limit is alpha. So this is equivalent to this, the limit of f as x approaches a is alpha. Okay, so if this and this holds, then this holds, and vice versa. Okay, next, as an exercise, let's prove the following equality. So E, Napier's constant, is equal to this limit. X goes to 0, 1 plus x to the power of 1 over x, which is equal to limit x going to positive infinity, 1 plus 1 over x to the power of x, and which is equal to limit x going to negative infinity, 1 plus 1 over x to the power of x. Okay, and if you remember, we previously proved that this Napier's constant is actually equal to limit of n going to infinity, 1 plus 1 over n to the power of n. Here, n was a natural number, but this case, present case, x is a real number. Okay, so there's a difference. Okay, instead of proving these three equalities, we first show that we only need to prove this one. Okay, so that is, first consider this one. So in order to prove this limit, 1 plus x to the power of 1 over x, this is equivalent to show the right limit and the left. Okay, e is equal to this is this is equivalent to show that the right limit of this is equal to e, and the left limit of this is equal to e. And for the first one, this right limit, let's put y equals to 1 over x. Okay, let's change the variables. Okay, then this one, this right limit becomes, if x goes to 0 from the right, then y goes to positive infinity, right? So y goes to positive infinity, and 1 plus, so x is 1 over y, and 1 over x is y. So this is same as this thing, okay? And for the left limit, we have a limit of x going to negative 0. That means to 0 from the left-hand side. And when x goes to 0 from the left, then y goes to negative infinity. So we have y going to negative infinity and 1 over y and y here. Okay, now let's change, let's say t is equal to negative y. Okay, so as y goes to negative infinity, t goes to positive infinity. So this is equal to t goes to positive infinity, and we have 1 minus 1 over t and to the power of negative t. Now, to the power of negative t is this. Limit t goes to positive infinity, and let's say, so 1 minus 1 over t is t minus 1 over t to the power of t. And this negative power can be made to positive power by swapping the numerator and denominator. So it's t over t minus 1 to the power of t. Now, and the numerator, subtract 1 and add 1. Okay, so we have t minus 1 here, t minus 1 here, and 1 is left. So t to the infinity and 1 plus 1 over t minus 1 t. Now, let's split one of these things into another quantity, another factor. So 1 plus 1 over t minus 1 to the power of t minus 1 times this. Okay. Now, at this point, for example, let's say let's put s equals to t minus 1. Then if t goes to infinity, then s goes to infinity also. So limit s goes to infinity and 1 plus 1 over s to the power of s times 1 plus 1 over s. So this factor converges to 1 as s goes to infinity. So we need to only consider this part. Okay, but this is actually same as this, right? Just difference is just a variable, but it's just a name, so we can just use whatever symbols we want. So after all we need to show is that this E, Napier's constant, is equal to this limit. So let's do that. But for any real number x, there exists some natural number n such that n is greater than or equal to x, n is less than or equal to x, and n plus 1 is greater than or equal to x. So we can always find such a natural number such that it's between that natural number and that number plus 1. Okay, for example, if x is like 1.56, then we can put n equal to 1. Then this x is greater than or equal to 1 and less than or equal to 2. That is 1 plus 1, right? So something like that. We can always do this. So because of this, we have, so 1 over n plus 1 is less than or equal to 1 over x, which is less than or equal to 1 over n. And if we add 1 to everything, then we still have this inequality. Okay. And since we have this, let's take the powers of this. So this to the power of n, and this to the power of x, and this to the power of n plus 1. So these orders are maintained here. Now we are sandwiching this quantity by this and this. So what we can do now is to apply the squeeze theorem. So if we can show that this converges to E and this converges to E, then we can show that this middle thing converges to E also. So let's do this. And 1 plus 1 over n plus 1 to the power of n is this. 1 plus 1 over n plus 1 to the power of n plus 1 divided by this thing. Okay. As n goes to infinity, this numerator converges to E, and this denominator converges to 1. So E over 1, that is E. And this one, 1 plus 1 over n to the power of n plus 1. We can just split one of the factors out. Okay, so this to the power of n times 1 plus 1 over n. Okay, now we know that this converges to E and this converges to 1. So E times 1, that is E. So therefore, 1 plus 1 over x to the power of x converges to E as x goes to infinity. And we are done. Oh, by the way, it goes without saying that as x goes to infinity, this n also goes to infinity, right? So that's why we can still apply the squeeze theorem. Finally, we show the Cauchy criterion of the right limit. And first, let f of x be a function on an interval I that is semi-open interval between a and b. Not including a, but including b. And then this theorem says the right limit of f of x as x goes to a from the right exists if and only if the following holds. For any epsilon, there exists delta such that for all x and y in the interval, this interval, and 0 and x minus a is between 0 and delta, and y minus a is between 0 and delta, then the difference between f of x and f of y is less than epsilon. So what this means is that this difference converges to 0 as both x and y approaches a from the right. Okay, so this is the necessary and sufficient condition for the right limit exists. Okay, for the right limit to exist. So let's prove it. So it's a if and only if statement. So we need to prove both directions. Okay, so first, proving this direction is easier. So suppose the right limit exists. The right limit a plus 0 is alpha. Okay, so suppose this limit exists, then so that means for any epsilon, there exists delta such that for all x in the interval, if the difference between x and a is between 0 and delta, remember this is the right limit, okay? Then the difference between f of x and alpha is less than epsilon. So this holds. Now consider the difference between x and f of x and f of y. And assuming that y minus a is also within this range, okay? Then this is f of x minus alpha plus alpha minus f of y. And using the triangle inequality, we can split this into two parts. And this alpha minus f of y. But this one is less than epsilon, and this one is also less than epsilon because y is also y minus a is also between 0 and delta. So that's 2 epsilon. But epsilon was arbitrary positive number, so 2 epsilon is also arbitrary. So this inequality holds for any epsilon. Therefore, this converges to 0, and we have shown the right-hand side. Okay, so we need to prove the converse. That is a little bit more involved. So first, let us define a sequence, an, that is a plus b minus a over n. Okay, n is a natural number. Now, let's see. So we are assuming that that this condition is satisfied. Okay, so we have this epsilon that is any positive number, and for that epsilon we can find delta such that this holds. Okay, so let delta be such a delta, this delta. Then there exists some natural number n such that let's see, n times delta. So delta can be a very small number that is greater than b minus a. Remember, this is by Archimedes' principle. By Archimedes' principle. So this is a positive number, and this is a positive number. However small delta can be, we can always find large enough n such that this inequality holds. Okay, now, because of this, we know delta is actually, let's say, maybe opposite. B minus a over n is less than delta. Okay, so if natural number n is greater than or equal to n, then we have b minus a over n is less than delta, right? Because for capital N, we already have this. So if lowercase n is greater than that, then we also have this, right? So that means, so remember this sequence. So if n is large enough, then an minus a, which is b minus a over n, should be less than delta. And of course, by this definition, an is always greater than or equal to a, right? So actually, it's not or equal to, but it's strictly greater than actually. So that means an minus a is in this interval if n is greater than or equal to capital N. So for any m and n that are greater than or equal to capital N, we have f of an minus f of am. The difference between these two values is less than epsilon. But we can actually define another sequence, let's say bn by f of an, right? So this is just another sequence. So what this means is that this sequence is a Cauchy sequence. So bn minus bm is less than epsilon if n and m are large enough. So that means this is a Cauchy sequence. Therefore, the limit of this bn exists. So this exists. Okay, but this means this n to infinity and f of an is alpha. So So this limit exists. Okay, we are not saying f of x, that limit exists yet, but we are just saying that as a sequence of real numbers, this limit exists. So technically, this is not the limit of a function, but this is a limit of a sequence. Anyway, by using this, we can show that actually the limit of the function exists. Okay, so what we want to show is the difference between f of x and alpha, so this alpha, this limit, is less than some arbitrary small positive number. So this can be written as f of x minus a n plus f of a n minus alpha. And let's see. Again, we use triangle inequality. And f of x minus f of a n plus f of a n minus alpha. And for this one, it's less than epsilon. For this one, we can use that Cauchy criterion. That is, we can assume that this holds, okay? Now, we can assume that x minus a is between 0 and delta. And if n is large enough, we can assume that an minus a is between 0 and delta. So that means this quantity is also less than delta, less than epsilon, I mean. So this thing is less than epsilon plus epsilon, that is 2 epsilon, which is just an arbitrary positive number. Therefore, the limit of f of x as x goes to a from the right is equal to alpha. This alpha is this alpha. Okay, and we are done. Okay, so that's all for this video. See you later.